Hey everyone, Morgan here, coming back at you one more time, talking about today molecular orbitals. And I am going to inform you straight away from the beginning, this is not something that is tested on the AP exam. But I cannot teach a chemistry class that does not show you this, okay? It is tested on things like the Chem Olympiad, but it's going to give you a much better understanding of the chapter if we have been through it, even if they're not going to ask an exact question about it on the AP itself. So, molecular orbitals are a completely new approach to the ideas of bonding. And they say that when two atoms come together, rather than considering the atomic orbitals overlapping with each other, which is exactly what we've just been talking about on pages 7 through 10, instead of that overlap, what we're going to talk about is a new orbital that is going to form that is called a molecular orbital, separate and different from the idea of the atomic orbitals that we've been talking about, and they would only exist in a molecule, hence the name molecular orbitals. Okay, now, why is it that we need another model? The first reason is that localized electrons are a bad idea, and we were localizing electrons in that last model. We were saying they're between these two atoms or they're between those two atoms, okay? Not cool. Second reason is that model does not deal well with the concept of a lone electron, a free radical. And that's important. We need to talk about those also. And it gave no good explanation of the concept of bond energy, which we dealt with back in the thermodynamics chapter. Okay, so what are molecular orbitals? They are a combination of atomic orbitals in a molecule, and they are created when atoms combine. Sometimes they're referred to as an LCAO, okay, which is, it's an abbreviation, okay, don't even worry about it. Why am I even going there? Linear combination atomic orbital, but not that big a deal. Okay, so now let's review something also from the last sets of lectures, last pages 7 through 10. A sigma bond is overlap of two orbitals that both have S character in them. Now, that bond is going to lie on a direct axis between two atoms. Straight line, okay? The electron density, it's localized, not a good idea, is directly between the two atoms. Now, a pi bond is overlap of p orbitals that are not hybridized, they're unhybridized, where the electron density is both above and below the direct axis. Okay. Now, when we start to put electrons into these molecular orbitals, much the same way we did with electron orbital diagrams, we have to pay attention to Aufbau, Hund's rule, and the Pauli exclusion principle. Aufbau tells us the building up principle, German word. Electrons start in the lowest energy orbitals, and they go up into higher energy orbitals. All right? Hund's rule. Electrons will singly occupy degenerate orbitals. I'm not sure I've ever used the word degenerate when talking about orbitals. It means orbitals of the same energy level. Okay? And the Pauli exclusion principle. No two electrons can have the same set of 4 quantum numbers, or more easily understood, you can have one that's spin up, then the next one's going to have to be spin down. Okay. Now, two ideas we're going to use later on, and I just had some room on this page, and that's why I put them here. The idea of bond order. Bond order is the number of bonding electrons minus the number of anti-bonding electrons, we'll get to those in a minute, divided by 2. And the idea of paramagnetism versus diamagnetism. Paramagnetic substances are attracted to a magnetic field, and that is because they have lone electrons. Diamagnetic substances are not attracted to a magnetic field, and they only have paired electrons. Okay. Give you a second. Pause if you need to. All right, let's move forward now to page number 12. Okay. Now, on page number 12, we are going to be putting electrons into molecular orbitals. We're going to deal with homonuclear species only. Why? That is because the energy levels are the same for both atoms. You can do it for heteronuclear diatomics also. It's just getting a little bit more complex. So let's consider that these are graphs, energy going up in both of these situations, energy increasing. Now, here is hydrogen. Okay, in hydrogen, you have an H here, you have an H here, and each hydrogen comes in with one valence electron. And since a molecule is forming, molecular orbitals are forming. And out here we have the atomic orbital, which is on the free atom. And in the middle we have the molecular orbital. Now, when we talked about electrons as a wave function, we said that it's possible to have both constructive interference of that wave function and destructive interference. And when two electrons, like these two, come together and form a molecular orbital, you're going to have constructive interference and you're going to have destructive interference of those wave functions. And the constructive interference makes this, which is a bonding orbital. We're going to call it the sigma 1s. That is our description of that orbital. And that's the constructive. The destructive interference is going to create what we call an anti-bonding orbital. Now in this case, we have two electrons. They both go into this one on the bottom because we're following the ideas of Aufbau and Hund's rule. Boom, boom, two electrons, one orbital. That's a bond. That's great. Now, we can also do the same thing for helium. Each helium comes in with two electrons, and I'm talking about diatomic helium, He sub 2. And your first thought is, Morgan has really gone overboard. Diatomic helium doesn't exist. Yes, you're correct, and I'm about to show you why. Because first off, two electrons go into the bonding orbital, and they form a bond. And then two electrons go into the anti-bonding orbital, and they destroy that bond. They cancel each other out. Okay? Bonding will be constructive interference of the wave functions, lower energy than the original atomic orbitals, more stable. Didn't we say that before? Didn't we say that the reason two atoms form a bond is because they're more stable when they're together than when they are apart? There you go. And these are the anti-bonding, which cancel that out. Okay. Now, that's the only two scenarios we can talk about with just the 1s, which is hydrogen, helium. Anything bigger than that has more electrons. Now, for higher energy orbitals, there are a couple different ways. There are two different ways you can actually put these orbitals together. An experiment has shown us that the way I'm talking about here is the correct way. The atomic orbitals that are the 2s's come together and make a sigma 2s. That's the sigma 2s, and the sigma star 2s, which is the antibonding orbital. Then when the two p's come together, it turns out that the actual order of filling has the pi x, we'll call that the pi x, and the pi y first, and then the sigma 2p. And I realize this might be going against things that you think would be normal, but experiment shows us that's the order they fill in. This would be the pi star x and the pi star y, which are both antibonding orbitals. And then we get the sigma 2p star, which is also an antibonding orbital. And that's the order that the electrons go into those. Okay? Pause if you have to. Get caught up. Then turn on to page number 13. Okay. Now we are going to do some diagrams for 6 different diatomics. We're going to do, let's see, we'll do B2, C2, N2, O2, F2, and Ne2. So we're doing period 2 of the P block. All right, and in every one of these cases, I've kind of pre-labeled the 2 S's and the 2 P's coming together, and based upon this diagram from the previous page, we know that this one should be the sigma 2s, this should be the sigma star 2s, and I'm not going to label them all because it's just going to make everything too hard to read. And we also know for all of these that the energy level of the sigmas and the pi's are lower than the energy levels of the sigma stars and the pi stars. Boron. Boron has 3 valence electrons. They'll be in the 2s and one of them in the 2p. So spin up, spin down, spin up, spin down. That cancels out. Bond, anti-bond. We're done. These 2 will come into here. 2 electrons in bonding orbitals makes a bond. B2, if it exists, has a single bond. Nothing in these anti-bondings. Now in C2, diatomic carbon, which actually does exist in flames. I actually had a friend who did his master's thesis on that back in about 1965 at the University of Wisconsin. Okay, so we have a spin up and a spin down, a spin up and a spin down. Now I've got 4 electrons here in atomic orbitals. They're going to come into molecular orbitals. Spin up, spin up, spin down, spin down. So they go up, up, that's Hund's rule. Then they go down, down. That is both Aufbau and the Pauli exclusion principle. They don't go up to that orbital yet because that's a higher energy orbital, Aufbau principle. They have to be spin down. That's the Pauli exclusion principle. Now for N2, I've got yet one more. It's 5 valence electrons. And they go spin up, spin down, spin up, spin down. Spin up, spin up. Spin down, spin down, spin up, spin down. So this cancels this. Boom, gone. 1, 2, 3 pairs of electrons in bonding orbitals. That means a triple bond. Oh, wait, I'm not an idiot. Not much of an idiot. I know the Lewis structure for diatomic nitrogen shows a triple bond. There's proof of it. How about there for the diatomic oxygen? So I have my spin up, spin down, spin up, spin down. They cancel each other. Spin up, spin downs, down. And then I also have an up and an up. Now, this bond is canceled by that. 3 bonds, 2 electrons in antibonding, cancel that one. Oxygen that's diatomic has a double bond. There we go. Nice proof. F2. And what ends up happening is that I get a total of 1, 2, 3, 4, 5, 6, 1, 2, 3, 4, 5, 6, 7, 8 bonding, and 2, 4, 6, 6 anti-bonding. 8 minus 6, that's 2 electrons that are bonding. That's a single bond. Or that this bond is canceled by this bond. These 3 bonds, the first 2, are canceled by those 2, leaving me just that bond. Now for diatomic neon, I think you can probably figure out what's happening here. Spin up, spin down, spin up, spin down, they cancel. Up, up, down, down, up, down. Ooh, 3 bonds. Up, up, down, down, up, down, 3 anti-bonds. Oh well, that just canceled out, and diatomic neon does not exist. Okay, now, we're going to go on to page 14, but I'm going to keep this page handy because we're going to keep referring back to it. Now, for B2, what's the bond order? Well, if I go back a couple pages, I see the definition of bond order is the number of bonding electrons minus the number of anti-bonding electrons divided by 2. So here, I've got 1, 2, 3, 4 bonding minus 2 non-bonding. Okay, that gives 2 electrons. The bond order is 1. And in the C2 diagram, I can see a bond order of 2. For N2, I see 3. For O2, I saw 2, 1, 0. Okay, so bond order is essentially the number of bonds between 2 atoms in a molecule. And it's possible to get fractional values, which is cool because that helps us with explaining resonance. Now, when I look at these diagrams, okay, I see that boron has unpaired electrons in molecular orbitals. That makes it paramagnetic. Carbon does not, so it was diamagnetic. Nitrogen does not, diamagnetic. Now, oxygen does have 2 unpaired electrons. So that makes it paramagnetic. Fluorine, none, so it's dia. And for nitrogen, we could say it's dia, but it doesn't exist. So this is cool. Oxygen is paramagnetic and is attracted to a magnet, and nitrogen is not. I'm sure if you just search that on Google, you'll find some great pictures. They're in the Zoomdahl textbook also, of liquid oxygen being attracted to a magnet. So, the grand poobah of bonding, the guy who told us everything there is to know about it, Linus Pauling, and I showed you this before, The Nature of the Chemical Bond by Pauling. What Pauling tells us, during World War II, he was working for the U.S. Navy. He was too old to be drafted, wouldn't have passed the physical anyways because he's kind of a sickly guy. But he wanted to contribute to the war effort. He was willing to sacrifice for the war, unlike how we're willing to put on a mask when we go to Costco. Now, turns out nitrogen is not attracted to a magnetic field, but oxygen is. So Pauling developed a meter that they could put in submarines that could detect the ratio of N2 to O2 in the submarine and help to keep it as a livable balance of gases. Because if you got too much oxygen, flames, fires, and they allowed smoking on submarines back then, believe it or not. Okay, not enough, and everybody's on the floor twitching. Okay, that was an important contribution to the war effort. Okay, now I want to compare the molecule benzene with our two models. How would it end up looking, okay, in those two models? So first off, benzene is C6H6. We drew a Lewis structure back, I think, on like page 3, maybe page 4. Carbon, 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 carbon. Alternating double and single bonds. Hydrogens out here off of each of the carbons. I could just show you the picture, but I'd rather have you see it form and draw it. So each one of these carbons is attached to 3 things: the 2 neighboring carbons and the hydrogen. So that's sp2 hybridized. Okay? So what we're going to do is we're going to draw an sp2, an sp2, and an sp2. Then here I'm going to draw 3 sp2s. 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 And everything has got a nice single bond between them. Now, what next? I have a leftover P on this one, which I'll put there and there, and there and there, and get the double bond. Now this carbon still has a leftover P, which I can kind of draw like that, and this carbon has a leftover P, which I'll draw in the same orientation. I get a bond. Now this carbon has a leftover P, and this carbon has a leftover P, which gives me that other double bond. Now, one of the big problems with this is that I have localized electrons, and that's not cool. So now, in the molecular orbital model, it turns out that the electrons are delocalized. Or I can also explain this with the resonance model, okay? Because with alternating double and single bonds, I'm going to get resonance. So what happens is the electron density is just spread out evenly over all 3 of those carbons. I'm sorry, all 6 of those carbons. My bad. Did not mean to do that. Okay, so there you go. That's the whole idea now behind the molecular orbital model. There's some beautiful pictures of this in the Zoomed All textbook. Okay? All right. Have yourselves a good day. Thanks for tuning in. This is Morgan once again signing off.